Hello, welcome back to Curious Planet. Today we're going to do a deep dive on igneous rocks. This is a follow-up video to my first igneous rocks video, which is a little more surface level, just kind of bird's eye view of the topic. So if you haven't watched that one yet, I highly recommend watching that first, and then coming back to this one. But with that, let's get started. So one thing about igneous rocks is they come in so many different flavors, if you will, right? You have like this whole spectrum of igneous rocks that exists, but they all come from the same place, which is the Earth's mantle, right? So like, if we can imagine, we have the surface of the Earth up here, there's like a mountain. And then down here, you have all this super hot rock. Okay, it's extremely hot and it's under immense pressure. And that's why there's a common misconception that the mantle is all molten rock. That's not true. It's actually mostly solid, and then sometimes it melts. And when it does melt, it starts to rise to the surface or towards the surface. And if you remember in the first video, say this mantle plume stops here, cools and hardens and forms a rock, that's our intrusive or plutonic rock. And if this were to continue all the way up to the surface and maybe come out of the volcano and become emplaced here, that's our extrusive or volcanic rock. Okay, so why does the mantle melt sometimes? Well, there's a few reasons this can happen. One is, there's three levers you can pull to get mantle melting, right? You can either increase the temperature. Okay, that's obvious. You make something hotter, it melts. Or you can decrease the pressure. This is called decompression melting. The immense pressure underground is what is preventing this extremely hot rock from being liquid in the first place. But if that pressure decreases, suddenly there's nothing holding back this extremely hot rock from becoming molten. And the third kind of weird thing that you can do is you can add volatiles. So like the easiest example of this would be like if you were to introduce water down into this extremely hot rock, like it's not ready for that. It's so hot, and you're gonna put this cold liquid in there. It just makes the chemistry very unstable. And that's one way that you can get mantle rising. And I wanna make a whole video on tectonics. And when I do, we'll cover subduction zones. Subduction zones are the main reason you get water in the mantle. Because you have a cold, wet, oceanic plate being shoved under the continental crust and being introduced to the mantle. But we're not going to talk about that today. I just want to kind of throw out there the mechanisms that you can get the mantle to melt and rise and start forming the rocks that we're going to be talking about today. Okay, so like we were saying, all igneous rocks start here and end up sort of becoming this whole spectrum of different chemistries and textures. And that just all depends on like what point they solidify or lithify and turn into a rock, right? So if they stop here and form a rock, that rock's gonna be very, very different than a rock that stops here. And one thing that we can think about is like, let's draw our mantle plume. And let's think about like wherever this stops and hardens and starts to form a rock is going to determine that rock's chemistry. And one way that I kind of like to think about this is like, what if we rewound the clock completely? And we looked at the Earth before it like had a crust or anything, just like the earliest days of the Earth. So way back then, 4.5 billion years ago, the whole Earth was just a molten ball, right? In some sense, you could say like the first Earth was all mantle. And so that kind of simplifies this process, because we don't have to think about how this mantle material is moving through the crust and what's happening with the fractional crystallization and stuff like that. Like, we can just think like, boom, everything is mantle. Okay, so now what? Well, like, eventually the temperature is going down, right? Over time, it has to. We have this early hot formation, and then the cold vacuum of space starts to cool this down. So let's look at what happens when the temperature starts to drop in this molten ball. Well, the first thing that happens is that elements in the Earth start to lose energy. And when they do, they have to like look for a different form to take on. I don't want to go like super deep into thermodynamics in this video. I think I will in another one, but one thing to think about is like, when the Earth is just a big molten ball, there's so much energy in this system that all the elements they're just free to like fly around and do whatever they want. It's just like chock full of energy. They're free to do what they want. But when you start cooling the system down, they have to take on a more structured form with a lower energy state to maintain equilibrium with their surroundings, right? And so what do? What's the first thing that happens? You have alloys of nickel and iron. Okay, these are like the two heaviest elements that are in abundance in this system. And so they find each other and they join forces, and they form these really dense, heavy alloys of nickel and iron. And what happens? This is like a liquid hot magma ball. Now you have this solid metal floating around. Well, what happens is it sinks wherever it's at. And this is a sphere, so everything's gonna sink and coalesce in the middle. Okay, and then it solidifies into a metal ball. That's the core. We all know about the core. So what's the next thing that happens? Well, this pattern of elements finding one another and coming together to form a lower energy compound to match the decrease in energy that's happening as the molten Earth cools. It just keeps happening, right? This was the first one to happen. What's the next one? Okay, well, let's look at what the 4 most abundant elements on Earth are. Okay, oxygen, silicon, magnesium, iron. I don't know if it's in that order. It's probably not in that order. But those are the 4 most abundant elements on Earth. So they join forces. They make a mineral. They make a mineral called olivine. Okay, olivine is a ferromagnesian silicate. Ferro meaning iron, magnesium, silicate. Okay, silica and oxygen. This is like a super important thing for all of geology. Silica and oxygen are extremely abundant in the crust and the Earth. Like, it's just everywhere. And they form this compound, this structure. It's a triangle, a pyramid, and this is called a silica tetrahedron. Okay, the silica tetrahedron is the foundation for almost every rock forming mineral on Earth. Okay, so if you look at the chemical formula for rock forming minerals, at the end you're going to see some combination of silica and oxygen. All right, so let's go back to our elements coming together and forming compounds to meet the decrease in energy, right? First we had these nickel iron alloys. Those have coalesced. In the middle we have our core. Now we have iron, magnesium, silica, and oxygen. This forms our first mineral, olivine. Why is olivine first? Because I shouldn't have erased that. Olivine, that was it. olivine is literally formed with a single silica tetrahedron. That's it. And so because of that, you can cram a bunch of these together and it's super dense. Okay. Olivine forms in the deep mantle. This is the core. Remember, the whole earth is mantle at this point. Deep mantle, olivine is forming. After olivine comes like the next densest mineral. Here's what I want you to understand is, remember, olivine is a single silica tetrahedron. Okay, well, the next mineral to form, I'll just write it. Okay, pyroxene forms after olivine, but it's not just one silica tetrahedron, right? Like, so this next mineral uses more than one silica tetrahedron. These minerals form in chains, right? So there'll be like another and another, and they form chains of silica tetrahedron. They're called inosilicates. They form next. They are less dense than olivine because now you have like a whole chain of silica tetrahedrons that have to fit into a single mineral. You can't pack them as tight. They're not as dense. So, you know, pyroxene would be like here, okay? And this process happens over and over again, where the next mineral to form after pyroxene has to involve like even more complicated systems of these silica tetrahedrons in order to form, and they become less and less compact, less and less dense. They form later and later and shallower in the mantle and eventually the crust, right? Okay, so this whole spectrum of silicate minerals is starting to form from the deep mantle to the mid and shallow mantle, and then eventually to the crust, because again, this whole time, this whole process is being driven by a drop in temperature, a decrease in energy. That's why the increasing complexity in this crystal lattice has to be made to take on a lower energy phase or state to match this. It's the exact same thing as water freezing into ice. Okay, think about it like, you know, you have a pond and then winter starts to come. And so like then you have like just little ice crystals that start to form maybe around the edges or something, right? That's olivine. Just one silica tetrahedron, right? It's the first thing to form. It's the ice crystals on the edge of the pond. But we're getting into winter. The temperature is continuing to go down and down and down until eventually the whole pond freezes over and it's like a giant lattice of ice, right? That's feldspar. That's the minerals that form up here, right? And it gets to the point where the temperature has decreased so much that now we don't have a primarily molten planet. We have a crust that is always solid, and then a mantle that is usually solid, but can be molten. And that's this, right? Okay. Now let's bring it back here. The exact same process that happened here with all these minerals, everything I talked about here now applies to the rising plume of magma. It's the same exact process, right? So in this case, in the deep mantle, when everything's still nice and hot and elements are very mobile, the first mineral to form, our friend olivine. It's simple, it's dense, and it forms first. Then you have pyroxene, and then that whole spectrum of minerals that we talked about until you have your major crust forming minerals, which are complicated crystal lattices, full framework minerals that are forming up here. They're complicated, they're not dense, they're light. That's why they're towards the top. And yeah, they're typically rich in silica and things like that. And if you watch the first video, you'll recognize these terms down here. This is where our mafic rocks and minerals form. They're dark, they're silica poor, right? Deep earth conditions. And then here's where our felsic minerals form. Silica rich, light in color. These are stabilized up here at the crust. Mafic minerals, olivine makes it to the surface, and it does, but it's the first to erode. It's the first to form, and it's the first to erode. It does not like being at the surface, right? Whereas quartz, which is the last thing to form, if you remember from the last video, quartz is the very last thing to form, and it just like kind of infills where it can in veins and stuff. Last to form, also last to erode. It's super comfortable being up here. It's kind of unfair. It's like the last one to the party and the last one to leave. He just kind of hangs around. But yeah, like the further this mountain starts eroding into sediments and being transported, the sediments over here will be really quartz rich because all the other minerals will have like eroded away along the way. But that's a sedimentary rock topic, so we can do that another time. But I hope this all makes sense. And we're gonna move on to the next topic with igneous rocks. All right, that's all for this one. As always, leave your questions and suggestions below. And until next time, stay curious.